Okay, we finished chapter 2, where we briefly talk about how to do systems of differential equations. We have several principles we had there, and we basically migrated everything from one dimension to two dimension, and maybe even higher dimension. Now in chapter 3, we want to focus on a special type of system of ODE, which is called the linear system. First, let's talk about linear systems in general, how to define them, what kind of properties they have. And the first thing we want to talk about is linear system with constant coefficients. Usually when we talk about linear system, we are referring to linear systems with constant coefficient. That is something look like this. Let's say dx over dt equals ax plus by, and dy over dt equals cx plus dy, where c and d, a and b, are constant. So when we say linear system, usually we refer to linear systems with constant coefficients. Okay, that means this is a linear system. Basically because we have a hidden 0x here, but if we only see once for y, it's still linear. Technically, this is also a linear system because when we say linear, we usually refer to our y and x. We do not contain t. This is also linear, but it's not linear systems with constant coefficients. So we are not going to talk about this until probably the next class. Here we want to focus only on the constant ones. Okay? Several properties of what we have here. Number one. So this is linear, but not constant coefficient. Not with constant coefficients. So we don't talk about this. Okay? So now properties. The first thing is this is always autonomous if it's constant coefficient. Okay? If it's autonomous, which means we can talk about equilibriums, which means maybe we have existence and uniqueness of solutions, and the solution does not intersect with itself. Okay. Second, why do we care about those kind of things? Because it arises from the real-life application. A very typical one we have seen so far is the harmonic oscillator. Okay, where we have y prime prime plus py plus q prime plus qy equals 0. We let v equals y prime. Then what we have is which is v prime negative py prime, which is v, minus qy. From here you can see p and q are constants, and the first one has a constant 1. So this is a linear system with constant coefficient. So we do have applications, at least from here. Okay. Now number 3, what do we care about linear system? That's probably the most interesting one. That is whenever you see something like this, and if it's linear, we will have the property such that we can write it as a matrix notation. If it's nonlinear, we may not be able to do this. But if it's linear, we can write it as a matrix. So the whole thing can be rewritten as xy prime for both A, B, C, and D. This only works for linear, okay? So if it's a general linear system like this, we can still able to write it as a matrix. Something like this. It's very easy to do, but the matrix will depend on time. So the reason we want to focus on the linear systems with only constant coefficient is because then this one can be just written as a matrix with numbers, not matrix with functions of t. So for that reason, we can rewrite it into y as a vector prime equals A times y. Here A is a matrix. Okay, and AY is not the traditional multiplication, but a matrix multiplication. It's a matrix times a vector. And because it's a matrix, we can start to talk about properties of matrix, like trace, like determinant, like homogeneous systems, and like how to find AX equal to B and solve for X. Those kind of things, and of course, eigenvalue and eigenvectors. Okay, so that's what we want to do next in this chapter. That is resolve everything we had before, but this time in matrix form. All right. With all that in mind, we will focus on, for this chapter, only 2D system. But in the end, we will talk briefly about higher dimensions. Because once we visualize everything as a matrix, all the operations with respect to matrix, including eigenvectors, eigenvalues, works for any dimension of a matrix. For example, a 3 by 3, a 5 by 5. As long as you can find the correct applications, you may very well use what we have and generalize them to higher dimensions. Okay, so we will focus on 2D, but it can be generalized to higher dimension. So let's talk about how we do a 2D system first. All right. So let's analyze what's going on. The first thing is, again, qualitative, which is equilibriums. If I don't specify specifically, from now on, every time we say a system, we always mean that we have a linear system with constant coefficient. Okay? So the first one, how do you do this? For equilibriums, that's where x prime equals 0 and y prime equals 0. So the whole thing stopped moving, right? So it's the same as saying x prime equals 0 and y prime equals 0. The same as saying y equals a vector 0, 0, which is the 0 vector. So to solve for equilibriums, basically you just need to solve ay equals 0. This is something we are very familiar with. This is solving a linear system. More specifically, this is solving a homogeneous linear system. Okay, and here when we say linear system, we mean a linear system of linear equations in terms of matrix case. And then we don't have to solve it one by one. We can solve it as solving a matrix. Well, what do we have here? Number one, this one will always have the trivial solution. Y equals 0, 0. Because any matrix multiply a 0 vector is still going to be 0. Okay, so for linear systems with constant coefficient, you will have at least one equilibrium. Second, can you have non-trivial solution? Okay, which means can you have a vector y which is not 0, 0, but still it will satisfy ay equals 0? Well, that's where we can talk about solving a linear system, a system of linear equations using matrix, remember? For homogeneous case, we say usually it's not doable. So no, if A is invertible, which is an invertible matrix. You can try to recall what we had in linear algebra. Or we can say if the linear transformation defined by AX is 1-to-1, or we can say the kernel space is zero-dimensional or is only this. Or we can say all the columns of A are linearly independent. So we have a lot of tools we had before in order to solve this. So basically the answer is no. Okay. But yes, if A is not invertible. If AX is not 1-to-1, if kernel space is actually 1-dimensional or 2-dimension, or we have a lot of ways to say it. But the quickest way, okay, so we have a lot of ways to say it, but we want to pick a quick way. That is when we take the determinant of A and set it to be 0. Okay, so I want to write down the fact. This is just one way to justify if a matrix A is invertible. Okay, therefore it has trivial solution or not. It has non-trivial solution or not for homogeneous case. Okay, if this happen, invertible, not invertible, and for this one is no non-trivial solution. This one has, we do have non-trivial solution. So all we need to do is just check the determinant. Where the determinant is defined by, try to recall. We first write down the matrix. Second, we put a big bar here. And it's a number defined by A times D cross product minus B times C. Okay, it's going to be a number. And it will depend on it's 0 or not. So the determinant of this, or let's just say, let's use a notation, get familiar with it. 1, 2, 3, 4 equals 1 times 4 minus 2 times 3. Therefore, it's going to be -2, not 0. This one is invertible. Therefore, if you solve AX, it will only have trivial solution. Okay. Now 1, 2, 2, 4. This is going to be 1 times 4 minus 2 times 2 equals 0. Because the determinant equals 0, therefore AX equal to 0 has non-trivial solution. Okay, you're supposed to solve it. For this case, we call it we will give it a special name. We call the system is a degenerate system. Basically means you don't have complete information or redundant, actually not complete. You have redundant information. That means even though you see a 2-dimensional system, but actually the information you get is lower than 2 dimension, maybe only 1 dimension. Okay, so we already are starting to connect everything we had before about linear algebra to at least this part, that is determinants and solving a system of homogeneous cases. All right. Now you can see this one can easily generate to 3-dimension, 3x3 matrix, or even 5x5, or even higher. So that's good. All right. Later we will also try to introduce how to determine it's a sink source or node using additional properties about A. So sink node source using properties of A. That's for later. Okay. Number 3. Now we have the qualitative analysis for equilibriums and for type of equilibriums later. Now we want to talk about solving, actually finding the solution. If you see something like this, what will the solution looks like? Okay. Equivalently, we have the matrix format. Now we have done this before in one dimension, but this time we want to understand from a different perspective using matrix. So of course we need to use a linear property. The idea is quite simple. Suppose we know y1, y2 are solution of then y1 minus y2 is the solution of let's say this. We can actually write down this directly. Then y1 plus y2 is a solution. Very easy to check. If y1 already equals a y1, y2 already equals a y2, then very easily y1 plus y2 prime equals a y1 plus y2, which means this thing here satisfies the prime of it equals a times itself. So y1 plus y2 is a solution, no problem. Thanks to that a matrix operation is linear, and also the derivative notation is linear. Second, a constant times y1 is also a solution. Okay, and this is easy to verify. If you already have this, you just multiply both sides by k. Now, using the properties of scalar multiplication with matrix, with vectors, we can easily put this one in by switching the order. And you can see, okay, this is also a solution. All right, this is the first linear properties we have. That is, if you have two solutions, then all possible combinations, linear combinations of these kind of vectors are also going to be solutions. Then second, we will be able to find the general solution in the following way. Suppose we have two solutions. Are the solution of the linear system, then if we also have y1 at 0, y2 at 0 are linearly independent. Then, the general solution of which we can be written as y0 as a vector, can be written as y equals c1 y1 plus c2 y2. Okay. So basically, this one tells you how to find the general solutions of any kind of linear systems. That is, you just need to find the two solutions, okay, and make sure they are linearly independent. And how do you make sure they are linearly independent? You just check at first they are linearly independent. At some time, then they will be linearly independent all the time. Okay. After that, you just take a linear combination, okay, of these two linearly independent solutions with general constant. That will be all the possible solutions you have. All right. Okay. Oh, where is it? This is the case. Okay, that's what we have. Now, moreover, what I just said works for linear systems because we know, okay, we have two first order differential equation. Each one needs an initial value which will generate a constant. Okay, that's why we have two constant. Okay. Moreover, now if we are solving IVP, which is a linear system plus an initial condition. Okay, I made a mistake before I wrote this down, but actually what I really mean is the differential equation alone. That's where we have general solution. Okay, when y0 equals x0, y0, okay, then what we need to do is just solve for C1 and C2. Okay, which means you don't have any general constant anymore. You will be able to find C1, what C1 is and what C2 is by plugging in the initial condition as what we did before. Okay, so that's roughly how we are going to solve the whole thing. That is, write down the general solution with two possible constants, which can vary. But then if you give me the initial condition, all I need to do is just go ahead and plug in the initial condition to solve which two constants will work for this time. Okay. Think about it. First one, because linear, you can write everything into a linear combination case, thanks to the linear property of the original system. Second, you only need two constant because you have two derivatives. Each derivative needs one constant. So you do not need a C1 plus C2 and plus a C3 Y3. It tells you 2 is enough. Okay? And when you say 2, you need to make sure that the first one is not a multiple of the second one, which means they are linearly independent. Because if they are linearly dependent, even though you see two solutions, but one solution can be generated from the other solution, so you don't have enough solutions yet. All right, so let me write down all the things I wrote down. Number one, make sure y1 and y2 are actually two solutions, not just the same solution, in the sense of they are linearly independent. Okay, in two dimensions, this basically means y2 does not equal a constant times y1. Okay, and how do you make sure that? Well, try to think about this. You are trying to make sure y2t does not equal to this one times t for some t. Otherwise, this one equals this one for any t. They are linearly dependent because one is a multiple of the other. You just need to show this. And then for that, why not you just show this? Okay, that's the assumption we said in the theorem. That is, you need to make sure that y1, 0 and y2, 0 are linearly independent. But even if you just know that they're linearly independent at 0, you will know they're linearly independent for any kind of t. Okay, so that's already enough. Okay, second, this basically have a hidden thing. That is, number one, 2 is enough. Okay, number 2 is y is a linear combination. Actually, is all possible linear combinations. of y1 and y2, thanks to the linear property. Okay. Number 3, for initial value problem, you just need to solve for C1, C2. Then you will have the exact solution. Okay. All right. Now what do we need? We will try to solve this later. For now, I will just give you some examples of something we have done before when we try to solve in one dimension. Now let's illustrate this idea using a decoupled system we had before. We only know how to solve decoupled systems for now. So let's use it as an example. Okay, so let's take this system here. And y0, y at 0 is given by 2, -3. Let's solve this initial value problem. We are supposed to have two general constants C1 and C2 when we solve the first one to get the general solution, and then we plug in the initial value to solve for the two constants. That will be the process. Okay, so the first thing we want to do is, since we don't know how to solve it using matrix yet, we will know it later, we need to write it out as a decoupled system, partially decoupled system. Okay, then we have number 1, number 2. With that in mind, we realize, okay, the second one is self-sufficient. Therefore, y can be solved. We use the constant C1. Then we plug it back into 1. Then we have x prime. Then we can move this one to the other side and realize it's linear. We need an integrating factor, mu t. Multiply on both sides. Okay, the left-hand side become a nice, perfect product rule. That's what we want. The right-hand side, you combine e to the -4 and -2. T together, it's -6. Okay, now what you want to do is you want to multiply everything. Oh, you want to integrate everything. And finally, you end up with x equals -1/2 C1 plus C2. Here is a C2 when we take the integration. C2 e to the 2t. Okay. So finally, if you write it down, your general solution will look like this. Your x is this. Your y is this. Okay. Now what we can do is we can take all the C1 out because we want eventually we have C1 something plus C2 something, right? So put everything C1 together. And you don't have anything on the bottom, just put a 0. Then we have C1 -1/2 plus C2 e to the 2t 0. So we do have the final solution to be looking like a linear combination of two vectors, which looks promising. And these two vectors are looking like y1 is this, and y2 is this. Of course, to this one to be well defined, we need to make sure one is not a linear multiple of the other. Otherwise, they are linearly dependent. To check that, we just need to check independence at 0. So we have y1 0 equals negative 1/2 1, and y2 0 equals 1 0. You can check it by definition, but from here you can easily, there's no way you can write this one to be a multiple, linear multiple of this, because no matter what you do, the bottom cannot be 0. Okay, so they are linearly independent. Check. Therefore, the final general solution can be kept in this way. It's done. Oh, no. It's done. C1 vector plus C2 times a vector, well, these two vectors are linearly independent. Okay, so that's done for general solution. Now to solve the initial value problem completely, we just need the general solution. Y E plus C2 e to the 2t 0 equals the initial condition 2 negative 3 at t equals 0, which basically just asks C1 negative 1/2 1 plus C2 1 0 equal to negative 3. Okay, which is, if you want, you can write it into a matrix form. And by that, we automatically know, wow, this is easy. This is probably section 1.1 in linear algebra, solving linear systems. Okay, you can use echelon form, you can use all kinds of fancy skills you have. Go ahead and solve it. You will find C1 equals negative 3. Let's see. C1, no, let's see. Be careful. C1 equals, let me write it out. C1 plus 0 equals negative 3. So C1 equals negative 3. Negative 1/2 C1 plus C2 equals 2. C1 is already negative 3, so C2 equals 1/2. Therefore, your final solution is going to be negative 1/2 C1, but it's already negative 3, so y1 plus C2 y2, that's what we got before. Now we can plug in this is 3/2 negative 1/2 E plus C2 2t 0. Okay, that's basically what we got from doing. What do I have here? Something is wrong. Oh yeah, there's no negative 1/2. That's why. Here. So we have negative 3. We have C1 plus C2 here already. Okay, negative 1/2 is actually here. I mixed them. So we have this plus that. When we finish, we solved everything. We finally have this negative 3 thing. Okay, plus 1/2 this. This will be the special solution for the initial value problem. Okay, so we found the general solution first, and then we go ahead and try to solve the constant C1 and C2 using the initial values. Plug them in, you have two equations, you solve it, and basically you're just solving a linear system. of matrix equations. All right, so step 1, general. From here we can see, well, we do have 2 linearly independent vectors, and we take all the possible linear combinations with them with 2 free constants. Initial value is just fix the 2 free constant to get the initial value we want. Of course, but how do we get these 2 vectors y1 and y2? We took a trick. That is, we have a partially decoupled system, so we can solve them separately. Of course, in general, your matrix won't be so nice. Your matrix will be something like this, which is not decoupled. So we are looking for a way to get y1 and y2 directly from matrix. We don't want to actually, decompose them into 2 individual differential equations and solve them separately. We want to solve them all together using the property from the matrix. That will be what we will be doing for the rest of the chapter. Okay, that will be all for today.